You know, when you look at the soft, magical glow of a firefly, and then you look at the super sharp, brilliant screen on your phone, you probably think they're worlds apart, right? Well, it turns out they're not. There's a direct line connecting that little bit of nature's magic to the high-tech screen in your hand. And it all comes down to how both of them create light from scratch. So let's just ask it straight up. What do they have in common? The answer here, it's not just some fun trivia. Nope. It's actually the key to understanding one of the most important pieces of tech you use every single day. And to get there, we're not starting in some clean room or a high-tech lab. We're starting out in a field at dusk. You see, to really get how our screens work, we've got to go back to the original blueprint, the one nature perfected millions of years ago for creating light without any heat. And the big idea here is a concept called luminescence. All it means is light without fire. It's cold light. A firefly makes it happen with a special chemical cocktail. That's called chemioluminescence. Our screens, they do the exact same thing, but instead of using a chemical reaction, they use electricity. We call that electroluminescence. It's the same exact principle, just with a different power switch. Now here's where it gets cool. That one little difference, using electricity to make light directly, is why OLEDs just blow older screens out of the water. Compared to the old LCDs, they're way faster, you can see them from any angle, and they're simpler to build. But the real game changer, the thing you notice immediately, is the black levels. An LCD screen is always on. It has a backlight, so black is really just a dark gray. But with an OLED, each tiny pixel can turn completely off, and that gives you a true, deep, perfect black. So how in the world does a tiny OLED pixel actually do that? How does it create light? It sounds super complicated, but it's really just a beautiful four-step dance happening at a subatomic level. Let's break it down. Okay, step one, you apply a voltage, zap. That current injects two different kinds of charges into these special organic layers. You get negatively charged electrons, and you get their positive partners, which are basically just a spot where an electron should be. We call those holes. Now, when an electron finds a hole, they smash together and recombine, creating this super energetic, unstable little thing called an exciton. To chill out and get stable again, the exciton has to shed all that extra energy. And how does it do that? It spits out a particle of light, a photon, and that is the light you see. Let's make that even simpler. Imagine the organic material in your screen has two energy floors in it. The top floor is called the LUMO, and the bottom floor is the HOMO. The electricity's job is to push electrons onto that top floor, the LUMO, and to create holes on the bottom floor, the HOMO. When an electron on the top floor sees an empty spot below and drops down to fill it, boom, that drop releases a burst of energy in the form of light. It's really that simple. A drop from a high floor to a low floor creates light. And this whole process is what makes an OLED so different from, say, a regular LED light bulb. A traditional LED uses these rigid, inorganic crystals where electricity flows super smoothly. But in an OLED, the O stands for organic. It's made of thin films of carbon-based molecules all jumbled together. So instead of flowing, the charges have to literally hop from one molecule to the next. It's a totally different way of moving electricity around. Now, this idea had been floating around for decades, really just a scientific curiosity. It was interesting, but it wasn't practical. And then, in 1987, one single paper, one discovery, changed absolutely everything. You have to understand, before this moment, trying to get light out of these organic materials was a nightmare. It took hundreds of volts of electricity, and what you got was this pathetic, dim glow. It was so inefficient, it was basically useless for any kind of real-world product. It looked like a total dead end. And then two scientists at Eastman Kodak, a guy named Ching Tang and his colleague Stephen Van Slyke, published a paper that just blew the doors off the whole field. Their work was so fundamental, so game-changing, that the core ideas they laid out back in 1987 are still the foundation of every single OLED screen made today. So what was their secret sauce? What did they figure out? Well, it was a few brilliant things all at once. First, they used a clever, layered structure that made the whole process way more efficient. Then, they used incredibly thin films, which meant they didn't need nearly as much voltage to get things going. And finally, they were just really smart about picking the right materials to get those charges in and moving around. They basically took a lab curiosity and turned it into a real working technology. And once that 1987 paper came out, the race was on. It was incredible. The technology just exploded, moving from a science lab to our living rooms and pockets at a truly astonishing speed. I mean, just look at how fast this all happened. Just 12 years after that breakthrough paper, we had the first actual product you could buy, a display for a car stereo. A few years after that, in 2007, Sony gives us the very first OLED TV. And by 2014, the tech was so advanced we were already getting flexible screens in our phones. That is a ridiculously fast journey from discovery to your pocket. But even with all this success, there was a huge problem. A really fundamental flaw baked right into the physics of how these early OLEDs worked. Turns out, a massive amount of energy was just being wasted as heat, and nobody knew how to stop it. This here is the problem. It's called the exciton dilemma. Remember those energetic excitons that create light? Well, it turns out quantum mechanics is picky. When they form, only 25% of them, the ones called singlet excitons, can actually produce light. The other 75%, the triplet excitons, were duds. They couldn't make light at all. They just turned into waste heat. So what does that mean? It means the first OLEDs were hitting a physical brick wall. No matter how clever your engineering was, you were literally throwing away 3/4 of the electricity you were putting in. The absolute best you could ever hope for was 25% efficiency. That was the hard limit. So the big challenge became, how do we get that wasted 75% to give us some light? And scientists came up with two absolutely brilliant solutions. The first is called phosphorescence. It involves mixing in heavy metal atoms like iridium that basically coax those triplet excitons into glowing. The second solution, called TADF, is even more clever. It uses smart molecular design to basically recycle the useless triplet excitons back into the useful singlet ones that can make light. And those two solutions, phosphorescence and TADF, they're the reason we have the incredible displays we have today. They're what truly unlocks the full, mind-blowing potential of OLED technology. Because of those breakthroughs, the 75% problem, it's solved. Modern OLEDs can now harvest the energy from pretty much all of the excitons they create. They've achieved a near-perfect internal quantum efficiency of almost 100%. Basically, every single electron-hole pair we put in can now become a photon of light coming out. No waste. So think about that. We went from the gentle glow of a firefly to a technology that converts electricity into light with almost perfect efficiency. It's just an amazing story of scientific discovery. Which leads to the big question. Now that we've pretty much perfected the light source itself, what's the next big thing for the screen in your pocket?